All right, today we're going to go ahead and create what is called the mole map in our class. This is going to be a real handy reference for you. What we're going to do is show you how to convert from all the periphery units that we're going to use in the stoichiometry unit. Whether it's mass, measured in grams, over here to the right, the number of atoms, particles, or molecules, the volume of a gas at STP we're going to deal with, and then down at the bottom there, volume of a solution in liters. So, the idea here is that each one of these arrows is going to have an operation that you're going to do to convert from one to the next. So for example, going from mass to moles, we're going to have an operation where we're going to either multiply or divide by some number. And that's actually where we're going to start today. Using what we learned last class for molecular mass, we're going to go ahead and take a look at what kind of calculation we would do. Let's say, hypothetically, Sutton gave you 23.4 grams of hydrochloric acid. And Sutton wanted to know, okay, how many moles of hydrochloric acid is that? Okay. If you look from your homework last night, problem number 11 had us calculating the molecular mass of HCl, and we found that number to be 36.4609 grams per mole. In other words, if Sutton goes back into the storeroom, gets out hydrochloric acid, he wants to mass out exactly 1 mole of hydrochloric acid, he's going to get out 36.4 grams of hydrochloric acid. Now that's a little funky because hydrochloric acid is typically not a solid, it's a liquid, right? Okay? But let's overlook that for just a minute here. How can we take this molecular mass and plug it into my conversion up here so that units cancel out? What has to cancel out if we're going to go from grams to moles here? The grams does. So, and the number's always associated with the grams. So Sutton's going to put 36.4609 grams down below and 1 mole up above there. So I just took this conversion factor and I flipped it, yes? All right? And the reason I did that was so that grams and grams cancel out, and the only unit that I'm left with is just moles there. Questions so far? So if we go back to the mole map, okay, you look, we started in the unit of grams and we ended in the unit of moles. So if we go back to this mole map, going from grams to moles, this top arrow here, what operation did Sutton do? He divided by what? The molecular mass. Okay, where MM stands for molecular mass, or in some cases it'll be the atomic mass, correct? When it's just an atom by itself. Okay? So what do you think the operation is going to be going in the reverse direction if I start in moles and go to mass? Yeah, it's going to just be the opposite operation, multiplying by molecular mass. Now remember, molecular mass is unique to each molecule or atom that's out there, right? Okay? This 36.4609 that we used in this example is unique to hydrochloric acid. It's going to be different for each type of molecule, yes? So that's the calculation. Why we practiced that last time is now you're comfortable doing that calculation. You can easily convert from grams to moles and back. Yes? Questions? All right, the next conversion that I'd like to look at is the right side of the mole map. Number of atoms, particles, or molecules. What number did we just drill into your head the past 2 days? 0.022 times 10 to the 23rd. That is the number of atoms, molecules, particles in 1 mole, yes? So our conversion factor that we're going to use over there is going to be 1 mole equals 6.022 times 10 to the 23rd atoms, molecules, particles, whatever the appropriate unit is for the given problem. This number actually has a name associated with it. This is called Avogadro's number, named after the gentleman who did the calculation. Figure that number out. The symbol we use for Avogadro's number is a line that comes up, then goes straight down, and then goes straight out like that. Okay, it kind of looks like a twisted capital N or something. Okay? That number is this right here, 6.022 times 10 to the 23rd. So again, let's set up a practice problem. Let's say Sutton had 2.4 moles of mercury. And Sutton wants to know how many atoms of mercury that's going to be. Well, how can I take this conversion factor that we came up with right here and plug it into this problem so units start to cancel out? What has to go down below? 1 mole. Okay, and what has to go up above? The 6.022 times 10 to the 23rd as my physical number there, and the units that are associated with that number are molecules, atoms, particles, whatever's appropriate. Yes? All right. And again, I'm not worried about the actual answer to this calculation. That's not the important part. The important part is the process. What operation did I do when I went from moles to atoms? I multiplied by Avogadro's number, yes? So we go back to my mole map, okay, going from moles to number of atoms, particles, or molecules, I multiplied by Avogadro's number, yes? Okay, where Avogadro's number is 6.022 times 10 to the 23rd. So what's the operation I'm going to do in the opposite direction? Divide. Okay. Questions so far? All right, let's do a practice problem. You guys have the green sheet in front of you. Number 1 says how many molecules of CuSO4.5H2O are in 10.0 grams. So our starting point is 10.0 grams of CuSO4.5H2O. Okay. And my ending point is I want to get to molecules of CuSO4.5H2O. Okay. So when you look at your mole map, first thing you do is look at the unit that's associated with the number that you're starting with. Okay? We got 10 grams here. So we go back to this mole map. Where am I on the mole map? Left, right, or center? I'm on the left side to start. Now, we look at the unit that I'm trying to get to. The unit I'm trying to get to is molecules here. Where is that on the mole map? Center or right? It's on the right side. So we've got a two-step operation here, yes? We've got to go from mass, divide by the molecular mass to get to moles, and then we've got to multiply by Avogadro's number to get to the number of molecules. Correct? Everybody see the process there? So we're going to divide by the molecular mass. The molecular mass we calculated for homework. Who's got their homework handy right out there? We already did this problem, so we don't have to do it again. Number 18, what'd you get? 249.69 grams per mole. Okay, that's the first step. Divide by my molecular mass. Now, if we hadn't done that for homework, we'd have to actually make that calculation right now, yes? Okay. Now, the next step, we go from moles to molecules. What operation are we doing there? Multiplying by Avogadro's number. So 6.022 times 10 to the 23rd molecules per mole there. I'm very deliberate in the way I set up my problem so that my units cancel out. Grams cancel out with grams, moles cancel out with moles, and I'm left with just molecules as the only unit in my problem. I go ahead and do the math. What do we get? All right, sig fig wise, we've got 2 sig figs in our starting number, or 3 sig figs in our starting number, yes? So our coefficient should only have 3 sig figs in it. Yes? Everybody agree? Did everybody get this value? All right, excellent. All right, so now it's time to tackle the top part of the mole map here. Volume of a gas at STP. We're missing the units on this one. The units would actually be liters here. Volume of a gas at STP in liters. Now, we need to talk a little bit about what STP stands for. We talked a little bit about it at the beginning of the year. Standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. We have to, because gases, you remember our discussion back in August or September about gases are a much larger, molecules are much further spread apart for gases than solids and liquids are, which means they're easily compressible. So unless we standardize temperature and pressure for gases, it's very difficult to come up with a correlation between the volume of the gas and moles of the gas. So that's why we have to kind of set some standards, some parameters, to be able to make some comparisons. For your purposes in class, we're going to consider all gases to be at standard temperature and pressure until we get to our gas law unit in the spring. At that point, then we'll remove this parameter and start playing with all 4 variables and how does changing the temperature and pressure affect the volume and how does it affect the number of moles and so on and so forth. But for right now, consider this to be golden here. Okay? ATM, atmospheres. ATM is atmospheres. So if these two apply, standard temperature and pressure, 1 mole of gas occupies a volume of 22.4 liters. And it doesn't matter what gas, any gas. 1 mole of hydrogen gas or oxygen gas. Okay? So again, just like we did before, let's set up a practice problem and see how the units best cancel out. We have 2.4 liters of H2 gas. Okay, and Sutton wants to know how many moles of H2 gas that is. Okay, well here's our conversion factor that we have. Let's go ahead and plug that in there in an appropriate manner to get the units to cancel out. What has to go down below on our dimensional analysis? Yeah, the 22.4 liters goes here. The 1 mole goes up above. Liters and liters cancel out. Okay, and we get some number. The number, again, is irrelevant. It's the operation that we did. Going from volume of a gas to moles, we did what? Divided, exactly. So we go back to our mole map. Okay, so going from volume of a gas down to moles, we divided by 22.4. 22.4. Let's erase that, make it a little bit cleaner. 22.4 liters per mole. So what's the operation going to be in the reverse direction? Yeah, multiplication. We're going to multiply by 22.4 liters per mole there. Questions, questions, questions. All right, the last section of the mole map that we have to look at is down at the bottom here. Volume of a solution in liters. Let's go ahead and we have to kind of define a new term here to make this make sense for a lot of you. We're going to use a term called molarity. Molarity is a very fancy way of saying concentration of a solution. Molarity is measured in moles per liter, which can be abbreviated MOL over capital L, or you can even simplify it down to just be a capital M there. So how many moles of a substance do we have per liter of solution? That is a concentration there. Questions so far? So we're going to use molarity to convert between a volume of solution and moles. This value will always need to be given to you in these types of problems. You cannot come up with the molarity. It has to be given to you. You have to know how concentrated your solution is to be able to calculate either the volume of the solution or the moles that are contained within. An example problem. Let's say Sutton wanted to know how many moles were in a 5.00 liter solution of 12.0 molar HCl. By the way, you heard me say that term for the first time. This capital L, or capital M, excuse me, is molar. That's how you say that. Capital M is molar. So Sutton's going to start off with the 5.00 liters of hydrochloric acid. And he wants to know how many moles of HCl are in there. Okay? The thing you got to remember is that this capital M represents moles per liter. So another way we could write that would be 12.0 moles per liter there. Yes? Okay, so how can we take this and plug it in here so that units start to cancel out? Yeah, okay, the end result here is we're going to do a multiplication operation. Moles up top, liters down below, so that liters and liters cancel out. Okay? So when we go back to the mole map, okay, down here at the bottom, volume of a solution in liters, going 2 moles, what operation did I just do? Yeah, okay, I multiplied by my molarity. Capital M is molarity, which is moles per liter. So what operation am I going to do in the opposite direction? Divide by the molarity. Questions? Questions? Yes? So one problem I could throw at you would be give you the moles and give you the volume of solution in liters and ask you to calculate the molarity, right? Okay, because by definition molarity is always moles per liter. So one variation of these problems is give you both of those values and make you calculate molarity, which is then just a simple division problem. Yes? Any other questions? All right.